Now that we've got our chemistry base, what we're going to do is start pulling a lot of the information together to use it to figure out a couple things. One, what is an ion? How can the ion be shown with this Lewis dot diagram? And then more importantly, what does that tell me about an element's reactivity? So we've got a lot of learning targets that we're hitting in this discussion. As always, we've got our key ideas, our essential questions that we're thinking about. So we want to be able to know what an ion is and where it comes from. And then each one of these is kind of specific about an element and its reactivity after you get the hang of it. So all of those will be answered as kind of more practice questions at the end. So as we get started here, we want to know what is going on with the amount of electrons for each energy level. You might have noticed in our simulation that electrons kind of had a specific spot where they were going. We definitely know they are not in the nucleus. That's the center of the atom, so electrons stay out of there. But each ring that we have on this diagram, 1, 2, 3, can hold a specific amount of electrons, and then it's full, and it maxes itself out. So the first ring, the first level, can hold 2 electrons. So go ahead and put a 2 electron on your diagram there. And the second level can hold up to 8 electrons. Let's actually do this. We've got 2, we'll put the 2 electrons on, and then here we'll also put 1, 2, 3, 4, 5, 6, 7, 8. So we're getting a little visual of what those electrons look like. So that's the amount of electrons each one can hold. And as we get larger, the larger elements have kind of specific rules. We'll get to that. We're just going to start with the basic right here. So 2 for the first energy level, 8 for the second. And again, that's looking at the maximum amount of electrons that ring can hold. So why are these outer electrons so important? Well, it's important to think about because we want to know what the element is going to do when it encounters other elements. How will it react? And its goal is always to react and achieve that full outer energy level, or full outer shell, just like a noble gas. So these guys right here, group 8, their outer shell is full of electrons. So when we look at that atom's group number, what we're getting is an idea if the atom will gain electrons to get to that stable 8 rule, lose electrons to get to the stable 8, or sometimes we'll start to see that elements would rather share electrons because they can't totally give them up. And again, the goal is to get to that full outer shell with that stable 8. And again, that number is a pretty big deal. So per usual, there are a couple exceptions. The elements that are really small. So elements like hydrogen, which is 1, helium, which is 2, and lithium, which is 3, those elements are full with their first shell being full with only 2 electrons. So if you think back to that first diagram we did with the nucleus and then the energy levels holding 2 and then 8, an atom can be full at 2 if that's its only ring. So this helium atom is full with just 2 electrons. And hydrogen can be that way too, as can lithium. And so we'll diagram it out and get a feel for how that's full, even though it only has 2. So as these electrons are gained or lost, what we're creating is something called an ion. So that ion is no longer an atom because my protons do not equal my electrons. Because those electrons are gained or lost, I end up with this charge, either positive or negative. So when they gain or lose, like we said, the number of electrons are not equal. So here we can see sodium normally should have a charge of 0 with 11 protons and 11 electrons. However, it wants to get rid of that 1, and as an imbalance occurs, we end up with a positively charged ion. So as we start to practice and record these ions, we'll either list out the element name either as positive or negative. So again, there's an imbalance. Positive is going to have more protons, and negative is going to have more electrons. So it's all about the balance. So just like we practice calculating, getting them equal, now I'll be calculating but looking at the difference after the gain or the loss. So the big question then becomes, how do we know if they will gain or lose? What determines if they're going to be adding those electrons or losing those electrons? We're ready to try a few examples as we start to practice the process of determining will the atom gain or lose electrons. First thing we have to start with is the element's group number. So checking out the periodic table for sodium and oxygen, let's just start with sodium. So here's our sodium on the periodic table. We know it is part of group number 1, right here. And we also know that it has 11 total electrons. So 11 electrons, 1 found on the outer ring. So when I go back to my example here, for sodium, I want to start at the first shell, which I know can hold 2 valence electrons. Then I continue on. 3, 4, 5, 6, 7, 8, 9, 10, having 8 electrons in the second, and then 1 on the outer shell. So this sodium atom is in group 1, 1 electron on the outside. I need to think about, will this element be gaining or losing electrons? Well, here's what we know about elements. They are lazy. They like to do the least amount of work possible as they're gaining and losing those electrons, working towards their stable 8 rule. So the 2 ways that sodium can get to stable 8 would either be to gain 7 electrons to add to the outermost shell, or it could simply lose 1 electron on the outside here, making the second shell become the outer shell and therefore full with 8. So again, here are the choices: to either gain 7 electrons or lose 1 electron. And because atoms are lazy, they will do the easiest thing possible, which in this example is to lose 1. So this electron gets removed from the atom, electron lost, and the sodium now becomes happy and complete with that full outermost shell, the second shell now being 8. Over here, oxygen on our periodic table is in group number 6 with a total of 8 electrons, 6 on the outermost shell. So starting here, 6 on the outermost shell, 2 on the inner gives me a total of 8, and 6 valence electrons. Now again, atoms are lazy. They like to do the least amount of work possible. So the choices here would either be for the oxygen to gain 2 electrons to make the outer shell full at 8, or lose 6 electrons and make the first shell be the full outer shell. Again, being lazy, picking what's easier, best thing to do here is to gain electrons. So we're trying to find 2 electrons from another element to get to our stable 8 rule. So because each of those atoms are gaining or losing electrons, what we are creating is an ion. So we now have to think about what is the charge of our new particle. So to do that, we want to compare out the number of electrons to protons. So just a reminder, according to our periodic table, we knew that sodium had 11 protons and therefore 11 electrons. So that's how it began. So let's just visualize that a little bit. We had 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 protons, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons. So initially, this sodium atom over here was neutral. But as it was trying to reach its stable 8, it went and lost 1 electron. So as we think about that electron going away, we now can get a visual on how these numbers of electrons compare to protons. We get a cancellation of all of these particles except this one remaining proton. The charge of this sodium element now becomes Na, which is of course the element symbol, 1 plus, because that's the amount of protons we have left over from our problem. Over here, oxygen started out 8 protons, 8 electrons. Everything was balanced. Oxygen wanted to reach stable 8. It said, I need to do that by gaining 2 electrons. So again, thinking about the balance, 1, 2, 3, 4, 5, 6, 7, 8. That's what it started with. 1, 2, 3, 4, 5, 6, 7, 8. It it gained 2 more electrons. So these continue to cancel each other out, and I have 2 additional particles, which are negative, meaning oxygen is 2 minus. So the charge is coming from the imbalance of protons to electrons. They all started even, but changed to have a charge depending if they gained or lost. So overall, we start to see this pattern with charges forming of an ion. Atoms that gain electrons, taking in extra negatives, become overall a negative ion. So everything balances initially, but when more electrons are added, the charge becomes negative. And so we would write just the symbol of the element with the charge up here. So just like we did for oxygen, we gained 2 more, so we get oxygen 2 minus. We see the same thing happening then with all atoms that lose electrons. Losing electrons, meaning that there will be more protons in the mix. So just like our sodium atom that lost 1 electron, these continue to cancel out. I have a remaining proton, and my charge becomes 1 plus. Now again, these neutrons aren't impacted, and they don't affect the charge because they don't have one. Their charge is neutral. So that's kind of a long process. Let's think about a little bit shorter of a way to get there. We're going to use these symbols called Lewis dot. Lewis dot are a really easy way to think about outer valence electrons and determine if they will gain or lose. So these Lewis dot diagrams show the number of electrons, like we said, in that outer energy level. Super easy way to see the valence electrons. So instead of diagramming everything out like this one, we'll learn this Lewis dot shortcut. 3 steps to getting this Lewis dot diagram done. Step 1 is finding the element on the periodic table, locating its symbol, so boron, B, and locating its group number, which is 3. So step 1, chemical symbol, group number. Step 2 then is to create the diagram. What we do is we put the dots right around the chemical symbol, almost like an imaginary energy level. When we do this, we place our first electron at the top of the symbol. So boron was in group 3, has 3 outer electrons. So I always put my first one here, and then I work my way around clockwise. 1 on the top, 2 on the side, 3 on the bottom. So this gives me a quick visual, all right? Boron has 3 outer electrons, and then I can start thinking about, will it gain or will it lose? Now if I have an element with more than 4 outer electrons, like chlorine, which is in group number 7, over here, I then start to fill up my electrons in kind of pairs. So just like with boron, I start at the top, I work my way around each side, and then I start to double up, top, right, bottom. So there are 7 total valence electrons in my diagram. So a really simple, easy way to do this and get a visual of how many there are, and then think about, what do I have to do to get this atom to the stable 8 rule that everybody's working towards. All right, let's do a couple examples. First one here being magnesium. So finding that on the periodic table, we know magnesium is part of group number 2. So that means it has 2 outer electrons. So I start at the top, put in my first outer electron, and I work my way around clockwise, 2. That's it, I'm done. Now I have to think about, which would the atom rather do to get to that stable 8. That's the goal. Is it easier for the atom to be gaining 6 electrons, or easier for it to lose 2 electrons? Either gain and have its full outer shell be 8, or lose and have its next outer shell be 8. Easiest thing to do here, least amount of work, would of course be to lose 2 electrons. So I would say here, this atom would lose 2, and the symbol becomes Mg, and it lost 2 electrons. That means it has more protons, Mg 2+. So we've got 2 more examples here that we want to try as we practice with our Lewis dot and gain or lose. Here we are with sulfur for our first one in group number 6. So starting at the top, there's my first outer electron, 2, 3, 4. Then I start to double up, 5, 6. So I can easily see there are 6 outer electrons. Thinking about the atom's choice, will it either gain 2 electrons to get to that stable 8, or would it lose 6 electrons to get to stable 8? Easiest thing for the atom to do is, of course, gain 2. So it will gain 2 electrons. So now it has gone from a perfect balance of protons and electrons to now having 2 additional electrons. So its symbol stays as S, but its charge becomes 2-. Awesome. Over here we've got xenon. looking at it on our periodic table, xenon is here in group 8. So starting at the top, 1, 2, 3, 4, doubling up, 5, 6, 7, 8. Now again, the goal is to get to stable 8. So if we look at xenon, we're noticing, hey, it's already at stable 8. So what will this atom have to do to become stable? Nothing. The symbol stays as Xe, and the charge is 0, so I don't need to make note of it. It doesn't become an ion, it stays as an atom. So you have a handful of additional practice problems. Give those a try. Check out part of the video again if you need a reminder. There'll also be another video posted showing some of those additional examples. So check that out either to make sure you're on the right track or to help you get started.